I'm going to give you another example relate to this K-drop question. So in this case, instead of deriving K-drop, a K-drop value is given to you. So in this case, the K-drop will be equal to 0.000359291. So you have to understand what it means in terms of unit, which is the percentage of voltage drop divided per mile divided by kilowatt load. So you know that throughout the entire feeder, how much the drop will be in terms of percentage, in terms of amount, in terms of how much the kVA load will be. So this is sort of like alarm load. So the question is find maximum load for the allowable voltage drop. So to find out the voltage drop, it will simply using that number multiplied by 1.5 mile, which is the distance, multiplied by the alarm load here, 7500 kVA, which is approximately close to 4%. So when you see this constant number is so small, when you do the multiplication, don't forget to multiply by the kilo, because otherwise you make this number too small that it may not seem to look right at all. So once you find out the voltage drop, then you will see if the maximum allowable voltage drop is less than 3%, obviously in this case it's more than 3 already. So then we have to revert back to say what will be the power. Instead of 75 kilo kVA, what will be this number? So by assigning this voltage drop to be 3 and then divided by this constant times the distance, that gives you close to 5600 kVA in this case. So just another way how you look at the problem with respect to what kind of information is given to you, or how you do the calculation the other way around. So that's the K-drop factor example. So for the next couple of pages, I might not go through all this in detail. You probably can see it through by yourself, but I do want to make sure that you do understand that the derivations of all this voltage profile and power loss under this rectangular form. So you start with a rectangular form, and then we are gradually going to the triangular form, and hopefully the trapezoid form. So the assumption we make here is we have to assume that the feeder is three-phase, because it always will be, and then the cable size, what kind of cable size will be, and the open wire size and the spacing between the entire feeder is assumed. So, and the other thing that may not seem to be realistic, but you know, since the feeder is not there, yes, why not we just assume that the load flow is perfectly balanced and uniformly distributed at all locations. So uniformly distributed is the keyword. You have the current flowing from the substation I sub s. You're flowing from this where the x value is equal to 0, because you start at this point all the way to the end of the feeder, where then the x value will be equal to the total length of the. So recall the way how you learn from the calculus, the current flow through every small part of this will be the incremental change of current with respect to distance, right? So mathematically speaking, you can write the del di over dx equal to k, which is a constant change of value, right? This is a sort of the slope if you will have to plot the I versus x axis in the two-dimensional plane, and that's something you can get with the slope, the positive slope. So x distance from the circuit breaker, which is the feeder end, as a function of the sending end I current and the distance x. So we gradually move away from the feeder head until we get to the point of the x equal to L, which is the value, right? And then the current is going to change it when you get to go to every lateral part of the loads here, right? So mathematically, it can be expressed as ix1 equal to ix2 plus di. ix1, ix2, and then that's the difference between all the current. This is the current going to serve all of the distributed uniformly distributed load around this area. Right, so you can write an equivalent circuit because this is like going through that and then somewhere else, right? So this will be IX2, this is the DI, and then this is before entering the DI, which is IX1. IX1 equal to IX2 plus DI, right? I think I draw it here, so I'm just sort of doing the repeated things, but you got my point here. So this is all going through the algebra by doing the substitution when current at the receiving end is 0, because the L is equal to X equal to L, the same thing. And then substituting this value from this conclusion to that will eventually get you to the point of what you want to find out the total drop of the X, which will be half times Z times L times the current. So the current source here is really important because you need to find out how much the current will be. You need to find out what will be the distance, and then you need to find out the impedance information. So this is sort of like the capital Z combined, because that tells you how long is the feeder. And then this constant half is a key. So throughout all this derivation, regardless if that is the rectangular form, triangular form, or trapezoid form, those are the things that we are going to find out. The difference with the other two compared with this rectangular form is the constant. So the constant here is really crucial. First of all, you have to know what shape you are, and then you determine what kind of constant value that would be. So can you see that now? The IX2 equal to IX1 minus K dx. And then from the total feeder perspective, you have the receiving current equal to the sending current minus K times the L. So when the L equal to X, which is the end of the length, then the current will be 0, right? Because there will not be any current when you are at this point. The current will be 0. IR equal to 0, there will not be any current. And this IR variable will be simply replaced with 0. And if you do this number, organizes a little bit equal to IS minus K times L, the K value will be equal to IS over L. And since this is known, you're going to substitute it into this equation that gives you IR, which is the current receiving end, equal to IS minus IS over L times X. So this is the simplified version from this that result in the equation 1. So we have to tackle the problem one at a time. Right now we are going to find out the voltage relationship. So it can be concluded that the distance from the circuit breaker, equation 1, as you can see, is that when the IS is equal to, let's say, X is equal to the L, which is at the end of the length, then the current will be 0, right? When the length is equal to 0, which is in the beginning of the feeder head, the receiving current should be equal to the sending current, because you don't have to serve any load yet. So the point of interest here is that to find out the voltage profile, to differentiate the voltage drop with respect to distance, we can go through some differentiation by going through the dV, voltage drop with respect to the distance, which is dx. In this case, is equal to the current Ix times the Z, right? So we have the second equation. We substitute the one equation into the second. Why? Because we have the I information, right? So if you substitute this into the X, then the entire equation will become Is times 1 minus X over L times the Z. So this part is actually coming from this first equation. And then you move the dx to the right hand side before you actually start doing this integration. dV equal to this times Z with respect to dx. Then you begin doing the integration of the voltage drop. Start from 0 to the x, which is at any point of the distance, right? And so this dx will become this equation, and then if you go through this integration, I think in the end you'll see that this is a conclusion we make for the voltage drop, right? Similarly, for the power loss, it will be the same. So the power loss is the I square R, as I mentioned. So the Ix squared times R with respect to distance. So we know that we have to integrate the dx. So the current as a function of that geometry here have to be replaced with this equation, right? So that will be replaced here. You have the square here, and then the same thing we did for the voltage drop. We do it for the integration for power loss as well. You do the integration from Ix equal to 0 to L with respect to this function, and in the end you realize that it will be the total power loss will be just simply S squared times R times L, because you have 3 phase here multiplied by 1/3 of the constant that give you basically 1. So in planning, the rectangular form is actually quite a popular one. So without further ado, I'm going to talk a little bit about this one example so that you can get an intuition how we actually solve a problem like that. So this is a very interesting problem with one feeder from the main and then throughout the 2 load here, just 2 load. One going in from the feeder, and then 2 load here with 5,760 feet from the main feeder, and this is a lateral as we defined earlier in the first week of class. So the example voltage is to find out the voltage drop calculation using the K factor used with the primary voltage of 4.16 kV. So this time we have a lower value of a nominal voltage. And then you have total customer 144, consumption per customer is 3.6 kVA. And this is the kind of conductor you will be using. This might affect some calculation later on, is that how much this calculation the conductor will be used for the main and the lateral, so it will affect how much the ampacity will be, as well as possibly the impedance information, because of the choice you make for using different kind of conductor at different part of the distribution feeder. So to find out first we have to find out the annual peak demand, right? We know the number of customer, we know the number of consumption per customer. The product of these two will result in the annual peak for all of them consumption under this feeder, which is 518 kVA. So assuming that the power factor is 0.9, because you never have a perfect unity power factor for case like that. Sometimes we have a mixture of purely resistive load and possibly inductive load. So 0.9 lagging power factor is a pretty reasonable value to begin with. So the next thing would be we have to estimate how much the current flowing from this main and then to this 2 lateral. Now, well, the lateral current will be calculated as L over square root of 3 times VLL, right? This is the equation that we talked about earlier before, square root of 3 times VL line voltage and then the current, and then that give you the power. So we just move it around to find out this current, and that give you for 72 ampere for each lateral. And then for the main current is simply multiplication of 2, because based on KCL, the sum of the current going into that node will be equal, must be equal the current going out from that node. So 72 and the main current will be multiplied by 2, right? So you may wonder, how is it relate to the model that we developed? It's not even looks like a rectangular form. Well, I think this is a compressed version of the rectangular form with only 2 load uniformly, right? The definition of uniformly distributed could be means equal. So in this case, as long as they are equal, we can still apply the approach to that. So to find out the lateral between these 2 points, first we have to use the half equation multiplied by the k factors times the s value times the distance. So this is a conversion from feet to mile. Feet to mile. Why? Because we have the consistent unit in this k factors. K factor, if you look at the unit carefully, is actually in the mile. So the conversion is very important. And then this is the s value, right? So k times s times l, and we mentioned the voltage drop under this uniformly distributed rectangular model. You have to include the half constant. So basically, nothing is new here, except that you have to use the half value to multiply by the whole thing from the constant value. That gives you 0.847 voltage drop. Now that's just a drop in from this point to both of them, right? This is a drop for the lateral. We still have the part from the feeder head to that before the branch out to two laterals. This part we have to calculate. So this is simply a lambda here, so there's no half. So the only difference is that you have to plug in the right k value and the s value and the l value. So in this case you have a different k here because of the different conductors, right? And what is shown here in this chart is that you have a 4100 volt value correspond to the blue and the black, and that's how we got the 0.006 value. Substitute into this, and then the 003 is actually to the lateral. So to find out the total voltage drop between these two from the feeder head all the way to the consumer, then it's simply the summations of voltage drop at the main feeder and then the lateral, which is 3.885 plus 0.847. That give you 4.732 total voltage drop. So in this lecture, we sort of go through all these k factors of voltage drop, basic concept of circuit, and then the rectangular form of the model. For next lecture onward, we're going to talk about different shape, and we'll go through the same analytical derivations for power loss and the voltage profile. And I hope that giving you some example will help you to understand how to solve the problem better. And I will talk to you next class.